is we are now bridging Physics 2, or at least what we've been covering up until this point in this semester, and connecting it back onto Physics 1. Because we can now talk about the motion of a charged particle. The second portion of this class, we're going to move on to a brand new topic, and unfortunately, or maybe fortunately for you guys, it does require calculus, and so we're going to have to, and this lecture and likely next day's, or Wednesday's lecture a little bit early as well. Okay. Well, let's come back to the first portion. So uniform electric fields are an electric field that does not change in terms of space. The electric field is the same everywhere in a generic region. And that is of great importance specifically in a laboratory setting, and we're going to go over the reason why. A uniform electric field, as opposed to one that is not uniform, a uniform electric field allows us to really analyze a motion of a charged particle. And this is where we left off. And that's because we discussed that electrostatic charges apply forces onto each other. However, the mechanism of the interaction is actually innate electric field. As long as you have an electric field, you can compute a force, but then what does a force do? It makes an object move with a certain acceleration value. And from this acceleration value, then you can get the position and velocities, which is how we characterize a motion of just any different objects. This relationship, so these relationships, the kinematic equations, these are valid for under what conditions? Who remembers? What is it? You don't know? When are these equations valid? Who says always? No, it is not always. Yeah.
Was it when it was in equilibrium? It was like something was equal to 0.
Actually, yeah. No. It is not. It is not. Sorry, not
acceleration is constant.
Yeah, it's when acceleration is constant. When acceleration is not changing with time. We need a constant acceleration, meaning we also need a constant force. Well, how do you get a constant force with electric systems? You need a uniform electric field. If your electric field is one that is changing throughout space, well, as the particle is moving, it's going to be under different electric fields, meaning the force is going to be changing. As soon as the force changes, the acceleration changes, and these are no longer valid anymore. Okay? So this is why uniform electric fields are very, very desirable for laboratory settings. It allows us to actually analyze the motion of charges. And so this is the full sequence. Once you have the electric field, you can apply this expression here to get the force. From force, you can use Newton's second law, which is F equals ma, to get the acceleration. From the acceleration, we can use these kinematic equations, which we use in Physics 1, to get the relevant kinematic parameters of position and velocity, or any other parameter that you might be needing. Now, unfortunately, before we actually apply this in an example, I do have to cover one additional bullet point, and that is regarding the directionality. So let's say there's an electric field in this direction. And in this electric field, we put a positive charge. Which direction is it going to go?
With the charge.
What do you mean with the charge?
No.
With the electric field?
I think so. It's either with or against.
With or against?
Or
section from before was like perpendicular to? Is it with or against? Or none of the, or neither?
Away.
Away?
Do we have the charge of the source of the electric field?
No, you're just given the electric field.
So it's just a electric field.
Electric field in this direction.
Against. That's not the.
Well, I'll say 4.
Okay, let's see a show of hands. The options are going to be for, against, or neither, I guess. Who says it's for? Raise your hand. Who says it's against? Raise your hand. Who says neither? Raise your hand.
You guys
It is with.
can. Take it sounds.
Well, why is that? Remember, we drew electric field lines last time. Electric fields are from positive to negative. Positive to negative. So you can think of this scenario, this electric field, you can think of it as there's a positive electrode here and a negative electrode here, at which point this positive is going to go which direction? Towards the negative side, because opposites attract. So, and apparently you guys don't read your notes because I definitely wrote it a few weeks ago. The force for a positive is in the same direction as the electric field, whereas if it's negative, and you place it in the same electric field, it's going to go the opposite direction. So this was something important that you just needed to memorize. Once again, it was kind of by convention. So if it's positive, it goes with the electric field. If it's negative, it goes against the electric field. Now with this, let's do an example. Let's say you have 2 electrodes. With a diameter of 6 centimeters. And let's say they are spaced 5 centimeters apart. Let's say these electrodes are charged by transferring 1.0 times 10 to the 11th electrons from one electrode to the other. Given this information, we are asked these following questions. How long does it take for the electron to travel from one electrode to the other? So how long does electron take to travel across the electrode? Second question, what is the impact speed? So you're given information about electrodes that they have a diameter of 6 centimeters and they're spaced 5 centimeters apart. You're also told that the electrodes are charged by transferring some amount of electrons. Just by given this information on electrodes, we're asked about the motion of an electron. It seems like we don't have enough information to actually, answer this problem, because we're given information about the electrodes, but we're asked about something completely separate. However, it's this chain of logical sequence that we need to understand. Okay. So let's begin the problem with the correct visualization. So let's say we have let's change things up a bit. Let's say on the left-hand side, we have the negative. On the right-hand side, we have the positive electrode. So this electrode is going to have a charge of negative Q, whereas a positive is going to have a charge of positive Q. These Q's are the same. And how do you know that? Or how do I know that?
Is that the same diameter?
No, the same diameter would be the same area. How do we know that they have the same Q?
These electrons are transferred from one to the other.
Yes. Essentially, we took electrons from this positive electrode and gave it here. This lost charge the same amount of charge that this gained it. So they're going to have the same but opposite charges. It's like I took, $2 from you. You lost the same amount that I gained. Right? That's essentially what this is. So they're going to have the same Q. What is the electric field going to look like? Electric field.
From the positive to the
The
negative.
electric field is positive to the negative. And in between, we can approximate it as a uniform, so a single line will denote everything that we need to know. Now here, where are the electrons? Or at least the ones that can freely move, or more freely move.
Positive.
Huh?
Not on the positive side? Because they're being folded to the negative?
Yeah, so okay. I guess for more completeness, we actually needed to hook this up to some sort of a circuit, and it's the electrons that got drawn here, and then it got put over here. Now this has excess electrons. There's more electrons here. And so in this scenario, the electrons that can freely move are on this plate. And so an electron is going to move from here, and it's going to shoot across to the positive electrode, because opposites can attract. This is an electron. It is the information about this travel that we are asked about. So right now, the parameters that we're looking for is how long does it take, so that's a delta T question. But delta T under what constraint? Or what condition are we looking for to say is the final state of the delta T? That's when the electron travels, we'll call it a distance lowercase d. So we want the delta T corresponding to the distance that the electron travels is going to be equal to lowercase d. That's the first question. How long does it take? That's delta T. But delta T for what to happen? For the electron to travel across the electrodes, and that is delta x is d. What about the second question? We want to know what is the impact speed. We want to know v. The speed is v. V is equal to what? But v corresponding to t is equal to t final, or x, or delta x is equal to d. So notice, in these scenarios, we have the condition delta x is equal to d. This is what we want to be focusing on. So I know because we're in this section, this is going to be something that you immediately want to turn to, but let's say in the midterm, maybe it wasn't so clear cut. As long as you precisely define this, then you just need to work backwards. Because to get delta t or v, we're looking for delta x is equal to d. But how do you get delta x? Well, you're going to need some information. And that information, you know, from the kinematics, you definitely need the acceleration value. Well, how do you get the acceleration value? Well, you would need to then think of, Newton's second law. You would have F is equal to ma, and that is how you would get there. But then how do you get the force? Well, we are in the topic of electrostatics, and the electric field is what allows us to get the force F is equal to QE. Now, do we know enough information about the electric field, or enough information to get the electric field? Well, this answer is yes, because we talked about the parallel plate capacitor, which is exactly what we have. And the electric field inside of a parallel plate capacitor is given by this expression, eta over epsilon naught. That is the electric field that we are looking for. So this is equal to eta over epsilon naught. Well, what is eta? That is the surface charge density. It's similar to lambda. We talked about it. We talked about this before. Meaning, the electric field of a parallel plate capacitor is simply Q A over epsilon naught. Now we just need to ask, do we know each and every single one of these parameters? Yes or no? This Q is the charge of an electrode. Do we know the charge of an electrode? Well, we're given this many electrons were transferred from one electrode to the other. And so we can actually write this as the number of electrons times the charge of an electron. That's what total Q is, divided by the area. This is the area of an electrode. Do we know the area of the electrode of this problem? Well, what shape is the electrode? Well, if it has a diameter of 6 centimeters, then it is circular. So the correct way to visualize this is we have two circular discs like this, and this is the diameter. Well, that's the radius. This would be the diameter, which is 6 centimeters. So do we know the area of a circle? Yes, we do. It's pi r squared. Do we know epsilon naught? And that is in the handbook. It is the permittivity constant, 8.85 times 10 to the negative 12. So you have that in your handbook. So we have this, we have that, we have, well, pi is just pi. We know the radius and we know the epsilon naught. So we have enough information to get the electric field of our scenario. So then this is going to be 1.1? Yeah, 1.0 times 10 to the 11th electrons times the charge of an electron is 1.6 times 10 to the negative 19 coulombs per electron divided by pi. The radius is 0.03 meters, but we are squaring that. And epsilon naught is 8.85 times 10 to the negative 12 Coulomb squared, Newton meter squared in the denominator. and this should equal 6.39 times 10 to the third newtons per coulomb. But we weren't asked to just compute the electric field of the capacitor. We want to know things like the delta T and the impact speed. And to do that, we need the force. So F was equal to QE, where Q, what is this Q? What is a Q? Huh?
1.6 times 10.
Yeah, but what is it? What does that number represent? It's the charge of an electron. It is not one electron. I saw that in the quiz. Q is the charge corresponding to that electron, not the number of electrons. So the charge of an electron, it is in your handbook, 1.6 times 10 to the negative 19 coulombs, times the electric field, which we just computed, 6.39 times 10 to the third newtons per coulomb. Can somebody get this number for me? Calculate.
E negative
1.02. 1.02 times 10 to the negative 15 newtons. Is that large or small?
Big.
Huh?
Small.
Are you sure? Well, let's see, because what does large or small mean? Large or small is a relative answer. Let's look at the corresponding acceleration value that arises. We weren't asked about the force. We need the acceleration to get us the parameters that we're looking for. So F is equal to ma, meaning A is equal to F over N. We just computed the force, which is 1.02 times 10 to the negative 15 newtons, divided by M. What is M?
Mass.
Mass of what? What object is moving?
The electron.
The electron. It is the mass of an electron that is in your handbook. Mass of electron, right here. You see my cursor? Yeah, 9.11 times 10 to the negative 31st. Kilograms. And what does this equal? It is 1.1 times 10 to the 17th meters per second squared. Is that fast or small? Or fast or slow?
Fast.
Right, this is insanely fast. Meaning this force, even though on the absolute scale it might seem small, however, considering the amount of mass that it's using to accelerate, it's actually a very, very high amount of force because it's accelerating the electron extremely quickly. we got here, but we still need to find the kinematic parameters that we're looking for. So with the acceleration value, we know that we can use the kinematic equations. So we know that we can use delta x is equal to v naught xt plus 1/2 axt squared. Do we know delta x? Well, yeah, the specific scenario that we're looking for is d, so we know it. Do we know v naught x? The initial speed. Well, yeah, we can assume that it's just coming off the plate, so that's going to be 0. We just computed the acceleration. The only thing we don't know is the t squared. So, t then is equal to square root of 2 delta x over ax. And we know what delta x is, and that is twice the distance, which was 0.05 meters. The acceleration value was 1.1 times 10 to the 17th meters per second squared. And if you do that, you'll get a value of 3 times 10 to the negative 10 seconds. 3 times 10 to the negative 10 seconds. And so this was the how long does it take for the electron to travel, because this was the time corresponding to delta x is equal to d. So that would be the answer to number 1. But we're also asked about the impact speed. We want to know v at delta x is equal to d is equal to what? And so v f is equal to v naught plus, these are all x's, axt. We already mentioned that the initial speed is going to be equal to 0. And so the final impact speed then is simply the product of acceleration and the duration. So this is going to be 1.1 times 10 to the 17th meters per second squared times 3 times 10 to the negative 10th seconds, which should be roughly 3.3 times 10 to the 7th meters per second. So like I mentioned, this section really is Physics 2 meeting Physics 1. And because Physics 1 is a prerequisite, pretty much I could just, it is fair game to expect you to know how to use the kinematic equations. That's not something that you could just completely forget about. You'll get a few more practice problems in the problem set. But that is considering the motion of a charged particle. However, we considered a few other charged systems as well. So let's next look at the motion of a dipole and an electric field. So dipoles are pretty complex, and so quantitatively speaking, we're not going to do any analysis because the numbers actually get quite difficult. The only analysis that we're going to be doing is from the qualitative side of things, so we're going to keep everything conceptual. So let's first consider in a uniform electric field. So here we have an electric field, let's say it is off to the right. And we put a dipole that looks like this. How do you think this dipole is going to respond in this uniform electric field? Who thinks it will move with the electric field? Raise your hand. Who says it will move against the electric field? Raise your hand. Okay, who says something other? Raise your hand. Well then, what is that other?
Stays in place.
Stays in place. Who thinks it stays in place? Raise your hand. Technically, it's not wrong, but that's not the only thing it does, and will still be marked incorrect, because the proper answer is it rotates. Why does it rotate? Well, you have a positive and negative, one of which wants to go with the electric field, the other one wants to go against it. And so it's actually not happy in this orientation, but it will rotate so that it is in the proper orientation. It will rotate with the positive in the direction of E and the negative in the opposite direction. The reason why it does that, and it doesn't move, is we have the force of the positive and the force on the negative side. Because we have a uniform electric field, that means the electric field is the same all throughout the space. As long as the dipole was overall neutral at the beginning, the positive and the negative, they're going to have the same total amount of charge. So, here we could say dipole rotates because of F plus and F minus. Right, the forces are going to be pulling in the respective directions. However, then it stays in place because F plus and F minus are equal and opposite. Therefore, F net is equal to 0. Well, that's in a uniform electric field. That's the boring case. Let's make things a little bit more interesting. What about in non-UEF? Let's say we have a positive charge here, and a positive charge has an electric field radiating out, or it's radiating in all directions. And in it, let's say we put a dipole here. How would the dipole respond in this case?
It'll move slightly away from the particle.
Will move slightly away from the particle. Why would it move slightly away?
Because it'll go in the same direction as the field.
What do you mean it won't go? We have three different motions here. Vibration, actually get rid of that. We have two. It can rotate and then translate.
Oh,
So when you say it goes, do you mean rotates or translates?
both?
It goes away? You said further away?
Yeah.
How can it do both? Wait, I'm gonna.
Like,
It rotates. Oh, as it's rotating, it goes further away.
yeah.
But then
Oh,
which
wait, no,
direc-
never mind, it'll rotate, it'll just rotate because the negative charge will pull it back, I guess.
So it'll rotate which direction?
Uh,
The negative's gonna point where?
towards the,
Points towards? Okay, so first, yes, it will rotate. So we have a positive charge here, and it will rotate to align itself. So we have the negative and a positive.
And that's what we'll do first. Or is that it?
Yeah.
That's all it does.
Oh, but that's my question to you guys. Is there more, or are we done?
And could it spin? Could it start spinning? Because
What do you mean spinning? Like, just keep rotating or spin this way?
keep rotating if the charges camouflage not the same.
Why would it keep rotating? The orientation, this is already happening,
Oh, okay.
right? The negative is towards the positive, that's the way that it wants it.
So then I'll say it doesn't do anything.
So this is it? Yeah.
Will it hold the negative now towards the positive since it's now looking towards it?
Will it? That's my question.
I mean, yes, but
Why?
not sure.
Why?
Because now there's two opposing charges, there's a negative and positive, so they're gonna, or sorry, not opposing, attracting charges.
But over here, you could view this as there's a positive charge or positive electrode over here. But in this case, this was stationary.
Is it-
Sorry,
The electric field is generated by something.
okay.
And this is a uniform electric field, so you can envision this as a positive electrode here and a negative electrode over here.
I mean, it just.
But this was stationary.
It just depends on whether the force beneath is strong enough to actually push the positive charge on the dipole so far that it'll continue to spin. Otherwise, won't it attract the negative charge towards it?
No, in this case, I'm telling you, it will rotate
Yeah.
and then it will stay in place.
Okay, I'm talking about the.
Yes, and the question I'm posing to you is how come in this scenario you're saying it's going to move, however, in this scenario it won't move?
because the negative charge is closer to the positive point charge than the positive charge on the dipole is, and in the uniform electric field, there's no one charge on the dipole is closer to.
Yes, and it has to do with the uniformity. So, Maddie, what you're saying is correct. I was looking for the rationale behind it. It will rotate and then it will move toward the charge. And the rationale was what Fatima had stated. In the electric field for a point charge, you have a distance dependent electric field. It gets weaker as you go further away. Meaning it's stronger as you get closer. In this case, which one is closer?
The negative.
Right, the negative is closer, so there's going to be a stronger interaction. So we'll put it this way, this will be F negative, and to emphasize that point, we'll make the F positive much, much shorter. And it will begin to move closer to the charge because of that non-uniform electric field idea. So here we'll have this. And we can say it does that. Here, F negative is greater than F positive, and that's because R of negative is less than R of positive. Remember, point charges have a distance dependency. And so for the motion of dipoles, you actually do have to consider the scenario and then try to think about the different types of interactions that it can have and the strength of the electric field that the dipole is placed in. So here this will tell us, therefore, F net is not equal to 0. So in a non-uniform electric field, the dipole will rotate and it will begin to translate. Whereas in a uniform electric field, it merely rotates. And this ends the section on the motion of charged particles. This will be where the quiz and the problem set end. Okay. Everything we do from here on out, this will be next week's material. Okay. So the problem set and the quiz just focus on up to this point and that point only. All right, let's move on. I'm gonna merely introduce this section. This is a section that typically requires calculus. Well, I'm gonna have to skip some of those, so we'll introduce it and then cut it in about, I'll say probably 10 to 15 minutes. And this is what is called Gauss's law. Gauss's law. To introduce this section, let me begin with an example. Let's say you have a thin spherical shell with a uniform eta. So let me draw the scenario. So this is spherical, not just circular. Spherical is the three-dimensional sphere, right? Three-dimensional. And let's say the shell is positively charged. Now I'm going to ask you a question about this, where it should seem like you were given enough information to know the answer. But at the same time, you're going to be like, but I still don't think I know enough to know the answer. Let me just ask the question so that you can feel it as opposed to me just describing it. The first question I'm going to ask is, what is the electric field at the center? And the options are the following. This is multiple choice. Is it going to be A, 0, B to the left, C to the right, D up, E down, or F, none of the above? So at the center, what is going to be the electric field that arises from this spherical charged shell? Let's see a show of hands. Who says it is A, 0? There is no electric field. Who says B, it would be left? C, to the right. D up, E down, F none. Why would it be none? Because it always is.
I just don't, I can't see how it would be B, C, D, or E, so I just think it's either A or F, and I don't understand how there wouldn't be an electric field.
Would it rotate and just stay in the middle?
What would rotate?
I don't know, I'm assuming that maybe the electric field does some sort of, I don't know,
No, that's-
something that's not zero.
Well, the answer is 0.
No. Of course it is.
Well, why is it 0? Just apply symmetry. From here, there's going to be an electric field that way, but for every electric field, or every contribution here, there's going to be something from here pointing it the opposite way. And you just do it all throughout, right? For every electric field, there's a counter-electric field being generated. So the electric field at the center is going to be equal to 0. What about, let's say instead of the center, let's say it was, let's consider a point directly above it, and we'll call that point A. What is the electric field at point A? Let's see a show of hands. Who says it's A, 0? Who says it's B, left? C, right? D, up? E, down? F, none of the above? And the answer is clearly A. The electric field at point A is also 0. Let me ask a third question. Instead of being inside the sphere, let's now say we are outside of the sphere. We'll call that point B. What is the electric field at point B? Who says it's A? Raise your hand. 0. Who says it's B, left? C, right? D, up? E, down? F, none of the above?
How many people answered that time?
Huh? It is D. E is up. Now, Coulomb's law seems like we have discussed enough to actually answer this question. We have a charged surface, and we're asked about the electric field. Coulomb's law, we dealt with charged surfaces and the corresponding electric field. However, although I think Q1 should have been kind of obvious, although you I don't know, you guys are like, no, this is a trick question and it's not against it or something. Q2 and Q3 were not so obvious, provided you only had the information provided by Coulomb's law. This is where Gauss's law comes in. Technically, Gauss's law is not providing us any additional new information. Gauss's law, just like Coulomb's law, is giving us a relationship between charge and the electric field. However, what Gauss's law is doing is approaching the same topic from a slightly different approach, and he's going to give us tools where Q2 and Q3 become almost as obvious as what should have been Q1, as long as you guys didn't think it was a trick question. But this is where Gauss's law comes in. He's not providing us new information. He's just giving us some additional insight, giving us a different perspective. So some things that were not entirely obvious then actually becomes obvious. So this is what Gauss's law is. So Carl Gauss, what he did was he gave us a relationship between charge and electric field. This is the same as Coulomb's law. But many people's opinions is that Gauss's law is more elegant. And allows for further considerations. I prefer Coulomb's law, but I have the minority opinion. Okay, so I'm just giving you my personal opinion. This is a more general viewpoint. The reason why people prefer Gauss's law is that Coulomb's law suffers from a few limitations. So limits. The limits of Coulomb's law. So even though all problems can be solved so even though there is nothing that Coulomb's law cannot do, but not all of it is humanly possible, or humanly feasible, we'll say. But not, but most, we'll say most, are humanly impossible. Meaning that it simply takes too much time. So think about the problem we did with 3 different charges exerting an electric field at one point, and think about how long that problem took. And that was only with 3. But how many charges are there in real life, or real life objects? It's going to be close to Avogadro's number, and clearly you're not going to want to be spending so much time working on those things. Gauss's law eliminates the necessity to do that. So Gauss's law has a completely different approach, arrives at the same answer, whereas, or without having to go through the nitty-gritty of having to count each and every single individual charged particle. It also, Coulomb's law does not make these 2 questions entirely obvious, whereas Gauss's law will. So this is a limit of Coulomb's law. Q2 and Q3 are not obvious. Now, what was this alternate approach that Gauss used as opposed to this idea of forces? Gauss used this concept of flux. Flux. So let's define flux. Who's heard this word before? Flux. Flux. It's simply the idea that something is passing through an area. Passing through an area. In terms of the specific topic that we are discussing, of electrostatics, Gauss used what is called the electric flux. And so this is simply applying the idea of fluxes onto electric fields. This would be the electric field passing through an area A A that is perpendicular to the surface. So let's say we had a surface here. We can define a surface with a vector that is perpendicular to that surface. So instead of having to specify the XYZ plane, we simply denote a vector, and that vector is going to be perpendicular to the plane in question. And let's say there's an electric field, a uniform electric field, like this. What this electric flux is really wanting is the electric field that's passing through this area, but that is parallel to the surface, or parallel to the vector. So here we want E that is parallel to A. And we can denote this mathematically, where this capital Phi is used for the electric flux. This is going to be E dotted with A. And this dot is a dot product. It must be there. Where this dot product is simply EA cosine of theta. So you can get the electric field that is perpendicular to A by taking the dot product. And so how do we get the angle theta? Well, the electric field E is coming out of this direction. The angle between the two vectors is our theta. So Gauss's law is going to be using this concept of an electric flux, and that's what we'll get to on Wednesday. So let's make sure we know how to compute a dot product, and that will be the last thing we do today, so we'll do a very short example. So let's say you have a 10 centimeter by 20 centimeter rectangle with an electric field is equal to 200 newtons per coulomb, and theta is equal to 30 degrees. Simply, what is the electric flux? Well, the electric flux is the dot product of the electric field and the area vector, where the dot product we know is simply the magnitudes times the cosine of theta. Here we're given the magnitude of the electric field, which is 200 newtons per coulomb. Here we're also given the magnitude of the areas, well at least the length and the side, so which is going to be 0.1 meter and 0.2 meters, times the cosine of theta, and we're given the angle is 30 degrees. And if you compute those, then you'll get a value of Newton meter squared per coulomb. And that is the answer. So Gauss's law utilizes this concept of the electric flux, and we'll get more into exactly how on Wednesday. But we will end it here because this is a good enough introduction, and this is where the last class left off.
Just real quick, okay?
Yeah.
You have an example where we were looking at the delta,